All right, you've walked me right up to this same door before and stopped short of it, and now you've done it again. 2 episodes back, you hauled me down to the floor of a valley, any smooth valley on that whole landscape of energy you drew, and told me to zoom in until all the complicated shape blurred away, and what was left at the very bottom was always the same little dip. The shape of a spring, you called it, a thing pulled back harder the farther you shove it off-center. Then, last time, right at the end, you named the back-and-forth wobble that dip makes, called it the oscillator, the single most common motion in the whole universe, and handed it to tonight. So here I am, holding the ticket. But I'll tell you my mood up front. I don't believe you yet.
Good. Don't. What is it you don't believe?
The claim that it's all one motion. You keep reeling off this list, a pendulum swinging, a plucked guitar string, an atom trembling inside a solid, and calling them the same thing. And I think that's a con. Look at them. A pendulum is a weight on a string, swinging out in a lazy arc. A guitar string is a taut wire, blurring so fast you can't follow it. An atom I can't even see. They live in different worlds, at wildly different sizes. They don't look alike, they don't move alike, and you want me to accept that underneath they're all doing the identical piece of work.
That's the wall we take down tonight, and by the end, you'll be the one insisting they're the same, because you'll have watched why. Let me lay out the deal for the whole evening. Every one of those things you listed has a resting place, a spot it settles into when nothing's bothering it. The pendulum hanging straight down, the string lying still, the atom parked in its slot in the crystal. Leave any of them alone, and there it sits, doing nothing.
Fine, everything's got a spot it likes. So what?
So nudge it a little off that spot and watch what they share. Not how they look, what they do. That shared behavior has 2 stars, and the whole night is chasing them. The spring, which is the simplest thing there is that does it, and the one rhythm that, once you learn to hear it, turns up absolutely everywhere. Learn those 2, and that list of yours collapses into a single object wearing costumes.
2 stars. The spring and a rhythm. Okay, start me on the spring. At least a spring I can hold in my hand.
Then hold one. A block sitting on a table, a spring running from the block to a wall. Left alone, the block just sits. That's its resting place. The spring neither stretched nor squashed. Now grab the block and pull it away from the wall, stretching the spring, and feel what the spring does back.
It pulls. It wants the block back toward the wall, back home.
It does. And here's the first thing to really notice, because the whole episode hinges on it. The farther you drag the block out, the harder the spring hauls back. A little pull, a little tug home. A big pull, and it's fighting you hard. So the pullback isn't some fixed, steady thing. It grows, right in set with how far you've taken the block from home. Small stray, small pull. Big stray, big pull. Hold on to that growing. It's the key idea.
Got it. And it matches my hands. A spring stretched a long way yanks back meaner than one barely pulled. So the block wants to go home, and the more I've dragged it out, the more it wants it. Let go, and it snaps back to the resting spot. And that's the end of the story, surely. It goes home, and it sits.
That's what it ought to do, isn't it? It's where nearly everyone's intuition quietly stops. But it isn't what happens, and the reason it isn't is a word you already own from our very first episode. Let go of the block. The spring hauls it home, faster and faster as it comes. And by the time it reaches the resting place, where the spring's finally relaxed, pulling neither way, the block is moving. It's got speed. So what does a moving thing do when nothing's stopping it?
It keeps going. That's inertia, Newton's first law, the whole stubbornness of motion thing from the start of all this. A moving thing carries straight on unless something turns it. So the block doesn't politely halt at home just because home is where the spring quits pulling.
It can't. It's moving, so it barrels straight through home and out the other side. It overshoots, sails past the resting place and starts squashing the spring on the near side. And now the spring, compressed, pushes back the other way, hauling it home again. And the whole thing runs in reverse. Home, overshoot, hauled back, overshoot the first way once more, on and on.
And which piece of that is the one I'd never have guessed?
The sailing past. The trip home, anyone would predict. Of course, a stretched spring drags the block back. But the block reaching its own home and flatly ignoring it, blowing straight through, that's what fools people. That refusal to stop is the whole reason there's a rhythm here at all, instead of a single quiet thud.
So it doesn't settle at all, it rocks.
It rocks. Back and forth, back and forth. And there, that rocking, is your oscillator, built in front of you out of exactly 2 pieces. And I mean 2, you can count them yourself.
Let me try, because I think I watched them both go by. The first piece is the spring, the pull that's always aimed back toward home and grows the farther out you are. The second is the inertia, the block's refusal to just stop when it gets home, so it overshoots. Pull home plus overshoot, those 2.
Those 2, and nothing else is needed. Let me give them working names. The first is the restoring force. Restoring because it's forever trying to restore the thing to home, always aimed back, always growing with distance. The second is the inertia, the plain carrying on of anything already moving. Restoring force brings it home, inertia sends it sailing past. And here's the test that proves you need both. Kill either one, and the rocking dies on the spot.
Show me. Take away the restoring force, the spring. What happens?
Then there's nothing pulling the block home at all. Give it a shove, and it just drifts off across the table in a straight line and never comes back. No rocking because there's no home to rock around. Take away the spring, and you haven't got a lazy oscillator. You've got a thing wandering off into the distance.
And the other way, keep the spring but somehow strangle the inertia.
Picture the block with no carrying on in it at all. So reluctant to move that the instant the spring stops pulling, it stops dead. Pull it out, let go. The spring hauls it home, and the moment it arrives, with nothing to send it past, it simply parks. No overshoot, no far side, no rocking. It creeps home and quits. So, restoring force alone gives a thing that crawls home and stops. Inertia alone gives a thing that wanders off forever, and only the 2 of them married give the endless back and forth. That marriage is the oscillator.
Everything so far is a block on a lab spring, though. Give me an oscillator that isn't wearing a coil, something off a kitchen table.
Hold a stiff ruler flat on the edge of a desk, most of it jutting out over the air. Press the free end down and let it snap up. It doesn't spring back level and stop. It whips up past level, bends the other way, whips down past level again, and buzzes up and down until it fades. There's your restoring force, the bent ruler straining back toward flat, harder the more you've bent it. There's your inertia, the whipping end overshooting flat on every pass. No coil anywhere, and a spring's whole behavior. You've twanged things like that your whole life without once calling them oscillators.
That's cleaner than I expected. 2 ingredients, and I can feel why each has to be there. Now, you spent a whole episode building me that landscape of energy. Where's the block on a spring living in that picture? Because I'll bet you're about to tell me I've already seen this.
You've not only seen it, you drew it yourself last time and told me how it moves, without knowing this was what you were describing. The block on the spring has a potential energy stored in the stretch or in the squash. Plot that stored energy against where the block is, and you get a valley, low in the middle, climbing on both sides. The resting place sits right at the bottom. Pull the block out either way, and you're climbing a wall, storing energy, which is just why the spring strains harder the farther you go. And for the true spring, that valley has a particular shape.
The parabola, the one you zoomed down to at the bottom of every smooth dip last time.
The parabola. So the block on the spring is a ball rolling in a parabola valley. And you already know how a ball moves in a valley because you told me last episode.
I did. Down to the bottom, fast is there, up the far wall, slowing, until it stops for a blink at a turning point, back down through the bottom, up the near wall to the other turning point. Stop, come back. Forever between the two turning points. That's the block then. That whole picture is just the block on the spring.
Every bit of it. And now every bit means something physical. The turning points, where the ball stops out on the wall, those are where you drag the block to its farthest and let go, or where it's overshot to its farthest on the far side. And there, not moving, it's got no motion energy. Every scrap of its energy is stored in the stretched or squashed spring. All potential, no kinetic, way up the wall.
And the bottom of the valley, the resting place it streaks through at full speed, that's where the spring's relaxed, storing nothing. So all the energy's in the motion there.
All kinetic, no potential, racing through the middle. It's the trade you built last time. Potential and kinetic swapping back and forth, with the flat energy line you drew still sitting there, the total that never changes. Last episode's still picture, now set rocking. And there's a tidy tell hiding in it. The block is quickest right where the spring is doing nothing, and stalled right where the spring is straining hardest. Speed and strain forever swapping places, and through all of it, that flat total line never so much as quivers.
And I like that I can hold it either way, the force story or the energy story.
They're one motion said two ways, restoring force and inertia, or ball rocking in the parabola. The same thing, whichever's handier. Hold whichever you like, they'll never disagree.
Good, but so far you've sold me one thing, a block on a spring. That's a spring being a spring. You promised me a pendulum and an atom were the same as this, and I still don't see how a weight swinging on a string has any spring in it. There's no coil, no stretch. Where's the trick?
Here's the move that makes the oscillator king of all motion. Forget springs for a moment. Take anything at all that has a stable resting place, anywhere a thing will sit and, if you nudge it, come back. The pendulum hanging down, the string lying still, the atom in its slot. In last episode's language, every one of those is sitting at the bottom of some valley on the landscape, its own valley, with whatever weird real shape that valley has far from the bottom.
Right, each thing's got its own valley. And now you're going to lean on the punchline from last time, aren't you?
I'm going to make you say it. What does every smooth valley look like, right down at the floor, when you zoom all the way in?
They all look the same. That was the whole point. You take any smooth valley, however lumpy and lopsided it is from far off, close in on the very bottom, and the little patch down there always flattens into the same gentle, symmetric dip. And you said that shared little shape was the shape of a spring. So, oh, that's it, isn't it?
Say the rest of it.
It doesn't matter what the pendulum or the atom really is, far from home. Down at the bottom, where the small nudges live, every single one of them has a spring hiding in it. Because every valley bottom is that same little dip.
You just took the wall down yourself. That's the whole argument, and it's the reason the oscillator rules everything. Here's why the bottom of a valley behaves like a spring. At the very bottom, the ground is flat. No slope, so no restoring push. That's why it's a resting place. Nothing tips it either way. And see how sweeping this is. I never once told you what the valley was made of. Gravity, buoyancy, the pull between atoms, take your pick. The argument didn't ask. Whatever builds the valley, its floor comes out flat and its walls climb the same gentle way, so the same little spring is waiting at the bottom of every one of them.
Flat ground, no push. That was the whole reason a valley bottom was somewhere a thing could sit.
And you've already got the picture for it. the marble in the bottom of a bowl from last episode. Dead center, the bowl's floor is level, so the marble just sits there, untroubled.
Right, and tip it a little out the side, and it rolls straight back down to the middle. That was the stable resting place, the valley bottom that heals a nudge instead of running off with it.
Zoom in close enough on the bottom of any smooth valley, and its curve straightens out. Whatever lumps and lean the valley has, those belong to its far walls. Down here at the floor they wash away, and what's left is always that same gentle, even dip. A little bowl, the same on both sides. And because it's that even, stepping out works the same everywhere near home. Take a step out from the bottom, and the ground has tilted a little. A little slope, so a little push back toward home. Take another equal step, and the ground tilts by that very same amount again. So the push grows by the same amount again. Step out, more tilt, more push. Step out again, more tilt again, more push again. Equal steps out add equal steps of tilt, so the restoring push climbs right in step with how far you've strayed.
Even steps, so the pullback grows in proportion to the distance from home. Which is the Springs rule you showed me with the block?
The Springs rule, to the letter. And it's the rule at the bottom of every smooth valley, whatever the valley's made of, are pendulums, and atoms, are swings. They're all that same flat-bottomed, evenly climbing dip, down where the nudges are small.
Let me make sure I'm not being hurried past this. You're saying the pendulum, on a small swing, gets pulled back towards straight down by an amount that grows in step with how far out it's swung, just like the spring's pull grows with the stretch.
Just like it. And the atom, nudged in its slot, gets shoved back in step with the nudge. Same restoring rule for all of them.
And they've all got inertia, so they all overshoot, so
they all do the identical back and forth. The same restoring pull that grows with the stray, the same inertia to overshoot, and so the same rocking. One shape, one rhythm, hiding inside a pendulum and a plucked string and a trembling atom and a child on a swing. Things that share nothing on the surface and everything underneath. A weight on a string, a wire under tension, a speck locked in a crystal. Peel the surface off any of them and you find the identical little engine, a pull that grows with the stray and the mass that overshoots it.
then settle the thing I opened with. Where's the spring in a pendulum? There's no coil to stretch. What's really doing the pulling back?
Gravity, aimed the only way it ever points, straight down. Hang the bob and it rests at the bottom. Nudge it out to the side and now gravity has a sideways say, tugging it back towards straight down. And the farther out you swing it, the harder that sideways tug hauls it home. The Springs rule, played by gravity instead of a coil, and it's the same tale for your atom. No coil there either, just its neighbours in the crystal crowding it back into place, harder the farther it strays. Different machinery every time, the identical rule underneath.
And that's why you keep calling it nature's favourite. It's not that nature loves springs, particularly.
It's not that nature loves springs at all. It's that near any stable resting place, gently disturbed, everything becomes a spring. Jiggle the world softly, almost anywhere you like, and it rocks with that one motion. The favourite isn't a preference. It's just what's left over when you nudge anything gently.
Let me try to break it on something silly then. A boat bobbing up and down at its mooring. Is that your same motion, or am I reaching?
You're not reaching. It's your same motion, wearing water this time. Push a floating boat down and the water shoves it back up, harder the deeper you press it. A restoring force growing with the push. Let go and it rides up, overshoots the waterline, tips too high, sinks back and bobs. A boat rocking at its mooring is a spring made of buoyancy. No coil, no gravity arc, just water refusing to be displaced. Or a tall radio antenna on a car, whipping back and forth after you brush it. Or a skyscraper leaning and swinging slowly back in a high wind. Same restoring pull, same overshoot, at wildly different sizes and speeds. Get the eye for it, and you'll catch oscillators everywhere. Anything that sits at a resting level and gets shoved off it.
That does land. So the spring wasn't one example among many. It was the shape they're all copies of, down where the nudges are small.
That's the thing to carry out of tonight, if you carry nothing else. But you keep saying the words that matter, so I'll hold you to them. Down where the nudges are small. That's the scope of the whole story, and there's an edge to it worth naming.
Go on. Where does it break?
The everything's a spring story is the small nudge story. It's true right at the bottom of the valley, in that gentle, even-stepped little patch. But haul a thing way out, swing the pendulum up to a big, wild angle, stretch something near its breaking strain, and you've climbed far up the valley wall, out of the little patch at the bottom, into the real shape of that particular valley, which is not a clean parabola anymore.
And out there, the different systems stop matching.
They part ways. The spring rule was only ever the shape of the floor. Near the floor, everything's one motion. Climb the walls, and each valley shows its own true face. Keep that boundary in your pocket. I'm going to spend it in a few minutes, where it explains a surprise before it becomes a trap.
There. So, small nudges, everything's a spring, everything does the same rock. Tell me about the rock itself. What does the motion look like as it runs?
Smooth and repeating and even. The thing swings out, slows, stops for an instant at its farthest, comes back, races through home at full tilt, out to the same distance on the other side, stops, comes back, over and over, each trip a copy of the last. And there's a name for how long one full trip takes, out and back and out to the start again. The period. One full cycle of the rock. One tick of this particular clock.
I've heard frequency used right next to that. Same thing or different?
Two ways of saying one fact, flipped over. The period is the time for one full cycle, how long each rock takes. The frequency is how many cycles fit into a stretch of time, how many rocks per tick of an outside clock. Long period, few per moment. Short period, many per moment. A slow, ponderous swing is long period, low frequency. A fast little quiver is short period, high frequency. Upside-down versions of each other, carrying the same news.
Fine, period. The time for one round trip. Now, here's a question that seems too obvious to ask, so I'm suspicious of it. If I pull the block way out and let it go, versus barely nudging it, the big swing has so much farther to travel. Out to the far wall and back is a much longer journey than a little twitch near home. So the big swing has to take longer. The period gets longer the harder I pull. I'd put money on it. What am I missing?
Say it once more, as confidently as you can.
Pull it farther, one round trip takes more time. Bigger swing, longer period. More road, same kind of motion, more time. I'm sure of it.
Your money's gone. The period does not get longer. Pull it farther, and one round trip takes the very same time as a tiny nudge does. The big swing and the little swing keep identical time.
That can't be right. The big one has vastly farther to travel. How does it cover more ground in the same time without... Oh, unless it's moving faster.
There it is. You had part of it and dropped the rest. What did you drop?
The restoring force, the one that grows with distance. When I drag the block way out, I don't just give it a longer road. I stretch the spring further, so it hauls back harder, so it comes home faster.
So the big swing has a longer road, yes, but it's whipped along the whole way by a stronger pull. The extra distance and the extra speed are born from the very same stretch, and they cancel, dead. Big swing, long road, fast all the way. Small swing, short road, lazy all the way. Same time for the round trip.
And all that extra effort just vanishes from the clock.
It never shows up as extra time. You'd swear it had to land somewhere, and it doesn't. It all pours into a grander, faster swing that comes home on the same beat as the timid little one beside it.
And the thing that makes them cancel is the proportionality, the pull growing in exact step with the distance.
The springs rule again, the parabola doing the whole job. Because the pull grows in exact step with the distance, the speed up matches the extra road. Let it slip out of proportion and the trick fails. Hold the proportion and the period simply doesn't care how big the swing is.
Let me sit in being wrong for a second, because I was sure of that one. My mistake was counting only the distance and forgetting that the same pull which gives the long road also gives the extra speed. They come as a package, and they wash out. So a swing dying down, getting smaller and smaller, keeps ticking at the same rate the whole way down.
And that unglamorous fact is the entire reason you can build a clock out of this. A pendulum keeps the same time whether it swings wide or narrow. So you let it run down a touch, feed it the faintest nudge to keep it going, and it never loses the beat. The shrinking swing keeps time as faithfully as the full one. A motion whose period ignores how big it is a motion you can trust to count out the hours.
Give me a picture I can watch because my gut is still fighting this one.
Two identical pendulums, side by side. Pull one way out wide, pull the other only a hair off straight down, and let them both go in the very same instant. Now watch. The wide one comes sweeping down in a grand, fast arc. The little one barely stirs. And yet they cross through the bottom together. They reach the tops of their swings together. And they turn around together, in lockstep the whole way, the wide one racing to keep the appointment the little one strolls to. Same beat, wildly different swings. Let the wide one shrink over the afternoon, and it never once falls out of step with its neighbour. That, in front of you, is why you can trust a swing to keep time.
So that lockstep is the thing a clockmaker is really buying. A beat that won't wander as the machine ages and the swing sags.
That's the thing bought and paid for. Long before anyone could say why, people had noticed a swinging weight was the steadiest cheap clock going. Now you own the why. It lives down in the parabola, where the beat forgets the size of the swing.
All right, but you promised me an edge, and this reeks of where it lives. You said everything's a spring, only near the bottom of the valley. So this, same time no matter how big the swing, has to be a small swing thing too.
It is, and you've walked us right to it. The equal time property is exact for the true spring, the ideal parabola, and very nearly true for anything near the bottom of its valley, where the parabola's a good picture. But haul a pendulum way out to a big, dramatic angle, and you've climbed out of the little parabola patch into the real shape of the pendulum's valley, which sags away from the parabola out there. And where it sags, the restoring pull no longer grows quite in step with the distance. It falls behind.
And if the pull falls behind, the cancellation I just watched doesn't complete. The extra speed doesn't quite pay for the extra distance.
So a pendulum swung really wide actually runs a touch slow. Its big swings take a little longer than its small ones. The equal time rule is the small swing rule. That's its edge, and that's the only place your first guess comes true.
So my very first instinct, bigger swing, longer time, wasn't stupid, it was just early. Flat wrong for small swings, where the thing keeps its time, only creeping toward true way out at the big angles, where the spring picture's already breaking down.
A fair way to hold it. Your instinct was describing the far wall of the valley, and I'd sold you the floor. Near the floor, the period couldn't care less how big the swing is. Out at the big angles, the floor's parabola gives way, and the period starts, slightly, to grow. Wherever the oscillator reigns cleanly, it's because we're keeping to small nudges near the bottom.
So the plain headline is, it keeps its time, as long as you don't ask too much of it.
That's the headline. Keep the swings modest, and it's a metronome you could set your life by. Drive it to wild extremes, and it drifts, running a touch slower the wider it goes. Which is why anything built to keep time is built to swing small. You stay down in the parabola, where the beat holds rock steady, and you never let it climb into the part of the valley where the shape starts to tell. A good clock is an oscillator kept politely near home.
Good, so the period ignores how far I pull for the gentle swings we care about. Then what does set it? Something must decide whether this rocks slow and stately or fast and buzzing. If it isn't how hard I started it, what is it?
2 dials. Only 2, which is a small answer for such a general motion, and it's the last big thing to get straight. The first dial is stiffness, how hard the restoring force hauls back for a given displacement. A stiff spring snaps back fiercely. A floppy one pulls back weakly. Stiffen the restoring pull and the thing rocks quicker, snappier, higher pitched.
And the second dial?
Mass. How much stuff is being flung back and forth? Pile on more mass and the thing rocks slower. The extra inertia is harder to whip around, so every swing is more ponderous. Stiffer, quicker. Heavier, slower. Those two between them set the rhythm.
Let me get the directions straight because they pull opposite ways. Stiff makes it fast because a strong pull hurries it home. Heavy makes it slow because a lot of mass is sluggish to turn around. So a stiff, light thing rings fast and high, and a floppy, heavy thing sways slow and low.
Just so, and you can hear both dials in an instrument. Take a guitar string and tighten it. You've stiffened its restoring pull, and the note jumps higher because it's now rocking faster. Slacken it and the note sags because it's rocking slower. That's the stiffness dial right under your fingers. And the mass dial is the same instrument's fat, heavy strings sounding the low notes and the thin, light ones the high. More mass, slower rock, lower note. Every tuned string is those 2 dials set against each other.
Give me the mass dial in something I can feel with my hand, not just hear.
Hang a light weight on a spring. Pull it down. Let go. It bounces up and down briskly, a quick little jiggle. Now take that very same spring and hang a heavy weight on it instead, and do it again. This time it lumbers, up and down, slow and grand. Nothing about the spring changed. Same stiffness, same pull. But the heavy weight is more sluggish to fling around, so every bounce takes longer. Swap heft on the same spring, and you're turning the mass dial on its own, watching the rhythm slow while the stiffness sits untouched.
And you're going to tie stiffness back to the valley, aren't you? Last time you told me the steepness of a valley would matter someday, and this smells like someday.
Someday's arrived. Stiffness is the steepness of the valley, the sharpness of the dip at the bottom. Picture 2 valleys, one a tight, steep, narrow gorge, the other a broad, shallow saucer. Try the gorge yourself. Nudge a ball off its bottom.
The wall rears up right away, a strong pull back home for a tiny step out. So that's a stiff oscillator, snaps back hard, rocks fast. And the saucer, nudge a ball off the bottom of that and the ground barely tilts, a weak pull for the same step. Floppy oscillator, drifts back lazily, rocks slow.
You just read stiffness straight off the shape. The curvature of the valley bottom, how sharply it turns up, is the stiffness. Sharp valley, fast rock. Shallow valley, slow wallow. It's the same dial the guitarist turns, drawn as a picture.
So the whole rhythm is baked into the system, the steepness of its own valley and the mass it's swinging, not into how I kicked it off. Say that plainly because it feels important.
The rhythm belongs to the oscillator, not to you. Stiffness and mass are properties of the thing itself, its own valley, its own heft, and how hard you started it doesn't touch them, which is just the equal time property from before, seen from another side. So every oscillator has a rate it wants to rock at, sitting inside it whether or not anything's nudged it. We call that its natural rhythm, the beat it falls into the instant you disturb it, set by nothing but its own stiffness and mass. A gentle nudge and a violent shove wake the very same beat.
Pluck it gently or pluck it hard.
Same natural rhythm, a different size of swing. Hold that, its own private beat. Everything left tonight turns on it.
A private beat electricity carries around. Okay, but I have to raise the objection I raised last time, because it's staring at me again. Nothing rocks forever. A real pendulum winds down. A plucked string goes quiet. You've drawn me a thing that swings for all time, and I've never once seen such a thing.
Right where it went last episode. And you can answer this one yourself now. Nothing rocks forever because nothing is free of friction. The air dragging on the swing, the rubbing in the pivot, the faint chafing inside the bending string. And friction, we said, doesn't destroy the motion. It does what to it?
It scatters it. That was the couch grinding to a halt. Friction takes the one big organized motion and breaks it up into the tiny jigglings of countless little pieces. Heat. So the swing's clean back and forth is slowly getting parceled out into warmth. In the air, in the pivot, in the string. Moved, not lost.
That's last episode's friction, brought into this one. The leaking of the organized swing into heat is called damping. And here's what it does. Round after round, a little energy bleeds off into warmth, so each swing comes back a touch smaller than the last. It doesn't stop all at once, it shrinks. Wide, then less wide, then a small sway, then a tremble, then still.
And on the landscape, that's a picture I already drew, isn't it? The flat energy line sinking. As the energy bleeds off, the total drops, so the level line settles lower. And the two turning points creep inward because the swing can't reach as far up the walls. Down and down, until the line sits on the valley floor and the thing rests at home.
That's damping drawn straight into the picture. The level line drifting down as heat carries the energy off. Everything real sliding to rest in the bottom of its valley. It's the same picture from last time, only now the level line has somewhere lower to go.
And here's where I'd expect the rhythm to sag too. As it winds down, shouldn't it get sluggish? A tired swing feels like it should slow.
Careful, that's the natural guess. And it's a trap. For gentle damping, the ordinary slow fade of a swing, losing a little each pass, the rhythm barely changes at all. The swings get smaller, but they keep coming at very nearly the same beat, right down until they're too small to see. Because the beat is set by stiffness and mass, the oscillators own two dials, and friction hasn't touched either of those. It's only skimming energy off the top.
So the size of the swing collapses while the rhythm holds steady. A dying pendulum keeps good time nearly to the end. It just does it in smaller and smaller arcs.
Damping shrinks the swing. It doesn't, to any real degree, slow the beat. Keep those apart, and no fading oscillator will fool you. Now here are a few everyday ones. The plainest is a child's swing you stop pushing. It keeps going, but each arc falls a little shorter than the last. Same rhythm, dwindling, until it's barely rocking, then hangs still.
And the guitar string is that sped up.
The same thing sped up. It rings loud, then softer, then fades to silence. The sound dying away is the swing shrinking as the energy leaks into warmth and into the air.
So the amount of damping is really a dial of its own, from barely there to heavy-handed.
It is, and you can hear the whole dial in things you strike. Tap a fine glass or a bell, and it rings and rings. Very light damping, the swing bleeding away slowly, so the note lingers on the air. Tap a lump of clay or a thick wooden block, and you get a dull thud that's over before it began. Heavy damping, the swing snuffed almost the instant it starts. Same strike, same oscillator idea, only the leakiness differs. Long ring, barely damped. Short thud, heavily damped.
So sometimes you fight the fade, and sometimes you engineer it. All right, left alone, everything rocks at its own natural beat, and friction slowly eats the swing while the beat holds. That feels like the whole story of a lonely oscillator. What's left?
The best part, the part with teeth. Up to now, the oscillator's been a soloist, struck once, then left to ring and fade on its own. Now we do something different. We push it over and over from outside, beat after beat, refusing to leave it alone. We drive it. And the instant you start driving an oscillator, one thing rules everything: timing. Not how hard you push, when you push.
Timing. Okay, I feel like my body already knows this one. Give me the setup and let me try to call it.
Here's the setup, and it's the one everyone's felt. A child on a swing, you standing behind, and you're going to give the swing a series of pushes. Gentle ones, all the same little shove. The only thing you get to choose is when each push lands. And the swing has its own natural rhythm, the beat it wants to rock at, set by its length. So you can time your pushes to match that rhythm. A shove each time it swings back to you. Or you can push at some other rate, out of step with it. 2 ways to push. Tell me what each one does to the size of the swing.
Let me take the matched one first. Pushing in time with its own rhythm, a shove each time it comes back to me. Each push adds a little speed in the direction it's already going. And because I've timed it to arrive just as it starts moving away, every push builds on the last. Nothing's fighting me. So the swing climbs, a little higher each cycle, my small pushes stacking up. It builds, and builds big, even though each single push is gentle.
And the out-of-step pushing?
If I push at the wrong times, sometimes I shove it along, but other times I'm shoving against it as it comes at me, breaking it as often as helping. The pushes step on each other, so it never builds. It just stays small, jostled around near the bottom.
Matched timing builds it up huge. Mismatched timing keeps it small. Read clean off the timing. That building up when you match its own rhythm has a name, and it's one of the most important words in the whole subject. Resonance. Driving a thing at its natural beat, so small, well-timed pushes add into a giant motion. And feel why it has to build. Out of step, your pushes are a squabbling committee. Some helping, some fighting, the sum near nothing. In step, they're a single will applied over and over at the one instant it lands clean, each push arriving to find the swing a little bigger than the one before left it, and lifting from there. The same small shove every time, and a mountain of motion out the far end.
And it has to be its own natural beat, specifically, not just any steady pushing. It's the matching that does it.
The matching is the whole thing, and that's what makes the natural rhythm matter. Every oscillator has that private beat baked in by its stiffness and mass, and resonance is what happens when the outside driving lines up with it. Hit an oscillator's own rhythm, and it drinks up energy greedily, the swing swelling every cycle. Miss it, drive faster or slower than its natural beat, and part of your effort fights the rest, and it stays small no matter how long you go. The oscillator is fantastically choosy, huge to its own rate, next to nothing to anything else.
And this is the one I did as a kid, isn't it? Pumping my own legs to get a swing going. Nobody was pushing me. I'd kick out on some rhythm of my own, and it would climb.
That's resonance, done with your own legs. You weren't shoving off anything outside. You were throwing your own weight around, kick and lean, once each swing, timed to the swing's own beat. Time it right, and every little heave feeds the swing, and up you go. Let your timing drift off the beat, though, and you feel it go slack under you and start to die. Now you're working against the very swing you're trying to build. Every child on a swing is doing the resonance trick with their legs, learning the beat by feel.
Give me the dramatic ones. The swing I've felt. What are the others?
Here's a startling one. A wine glass and a singer. A wine glass, tapped, rings at a particular pitch. That pitch is its natural rhythm, the glass rocking as an oscillator. Now have a voice sing that exact pitch, loud, and hold it. The sound is a stream of pushes on the glass, arriving right at the glass's own rhythm. Resonance. So the glass's tiny rocking builds and builds, each sound push adding to the last.
Until the swing is more than the glass can survive, and it shatters.
No hammer, no touch, just a matched rhythm pouring energy into the glass, a little at a time, until it flies apart. The voice isn't stronger than the glass, it's only in step with it, over and over.
So it shatters itself on nothing but a held note. What's the big one?
A big structure, a bridge, say, is an oscillator too. It's got a natural rhythm, a beat it will sway at if something disturbs it, set by its own stiffness and mass. Normally the winds and loads pushing on it are a jumble of timings, out of step, and it just shrugs them off. But let something push it rhythmically, right at its own natural sway. A wind that gusts in time with it, or the structure feeding its own swaying back into itself, and you've got resonance on a terrifying scale.
Each little push adding to the sway growing.
And a bridge can rock itself to pieces, swinging harder and harder from pushes, no single one of which could have hurt it. There have been famous cases of a bridge that shook itself apart in just this way. A matched rhythm and small pushes piling into a motion big enough to tear the thing down. You can feel a gentle cousin of it on any springy footbridge. A crowd happens to fall into step, the bounce nudges everyone deeper into step, and the sway grows until people grab the rails, cured only when the crowd breaks stride and stops feeding the beat.
So resonance is both the useful thing and the dangerous thing. Same mechanism, pointed different ways. But wait, if the pushes just keep adding, does the swing grow without any limit? Forever bigger? That can't be right, or every bridge would fall.
It can't be right. And you've caught the thing that saves the world. The swing does not grow to infinity because damping is still in the room. Every real oscillator leaks energy to friction, and the bigger the swing gets, the faster it leaks. So, as resonance pumps the swing up, the leaking climbs to meet it, and they reach a standoff. The swing grows until the energy you're pushing pours in each cycle just matches the energy friction bleeds out each cycle. And there it levels off.
So the response is enormous, but capped. And the cap depends on how much friction there is.
A lot of friction, a modest peak. Very little friction, a frighteningly large one. That's why a well-damped structure rides it out and a lightly damped glass shatters. Same resonance, different breaks. The peak is always a real, finite thing in the world. But finite can still be far more than an object can bear.
So the unsettling thing about resonance is that raw strength barely enters into it. You don't overpower the oscillator. You outpatience it, feeding it crumbs on the beat.
That's the unsettling gift of it. A weakling in time beats a giant out of time. The giant's one huge shove lands at the wrong instant, and half of it fights the swing, while the weakling's feather-light taps land right on the beat, again and again, everyone keeping all its help. Timing, not muscle, the whole danger of the thing, and the whole use of it, in a single line.
And I'm guessing the useful side of this, tuning a radio, an instrument sounding its note, is the same choosiness turned to good.
The very same. A radio tuner is an oscillator you adjust until its natural rhythm matches the beat of the one station you want, and then it resonates with that station and ignores all the others crowding the air because they're off its rhythm. That choosiness, huge response to its own beat, near nothing to anything else, is what lets it pick a single signal out of the noise. And every musical instrument is built around parts that resonate at chosen rhythms to swell certain notes. So look at the spread of this one idea. A clock keeps time on an oscillator that ignores how big its swing is. A radio hears one station by resonating with it. An instrument sings by resonating at the notes it's shaped for. And the same trick, unwanted, can shake a structure to pieces. Drive at the natural rhythm, and a little goes a very long way, for you or against you.
Okay, I came in not believing a pendulum and an atom were the same motion, and I think I quietly changed sides somewhere back there. Wind it all up for me. I've got springs and valleys and swings and a shattering glass rolling around loose, and I want them handed back as one thing.
Here's the whole night in one breath. Near any stable resting place, nudged gently, everything is a spring, because the bottom of every smooth valley is that same little dip, a restoring pull that grows in step with how far you've strayed. Give that restoring pull a partner, inertia, which overshoots home, and you get the endless back and forth. The oscillator, the same rock hiding in a pendulum, a plucked string, a trembling atom, a child on a swing.
And its rhythm comes from just the two dials.
Stiffness and mass, the steepness of its valley and the heft it swings, and that rhythm is its own private beat, deaf to how hard you started it. Friction slowly scatters the swing into heat, so real rocking shrinks and dies while the beat holds steady. And drive it at its own natural beat, and small, well-timed pushes pile into a giant response. Resonance, capped only by that same friction. One shape, one rhythm, everywhere you look.
That's more unified than I expected when I walked in swinging at you, but you've got that look, the one that means you're about to open a door and leave me staring through it. What's next?
There's one thing left, and it's where we pick up next time. Everything tonight was one oscillator, a single spring, a single swing, a single glass, alone, minding its own beat. But nature almost never gives you just one. Look around. The atoms in a solid aren't one trembling thing. They're an immense crowd of them, each a little oscillator, every one joined to its neighbors. So the real question, the one that opens up music and heat and the whole physics of solids, is what happens when you tie oscillators together.
Tie them together how? Just a row of springs, all linked up?
A row of them, each joined to the next, so when one rocks, it tugs its neighbors, and they tug theirs. And the moment you couple them, something new appears that no single oscillator has. They start trading their energy back and forth along the chain, passing the swing from one to the next.
And out of all that trading,
and this is the astonishing part, and it's all I'll say tonight, the whole crowd can settle into special patterns where every piece rocks in step, the entire chain moving as one organized thing. Those shared patterns are the doorway to waves, to music, to how sound and light and heat travel through matter. The name for the whole business is coupled oscillators, and that's next time, not tonight.
a whole chain of them, all rocking in step. That doesn't sound like a footnote to tonight. It sounds like it changes the character of the thing entirely.
It changes everything, which is why it earns its own episode and not a corner of this one. Tonight you learned the single note. Next time, we build the choir.
Coupled oscillators. A whole chain of nature's favorite motion, talking to each other. I'll be here for that. But let me take one image out the door, because it's the one that flipped me. That wine glass, just sitting there, and a voice finding its one private rhythm and singing it, gently, over and over, each soft push landing right on the beat, until the glass is rocking harder than it can bear, and it bursts. Nobody touched it, it shattered itself, on its own rhythm. That's the thing I'm keeping, that everything's got a rhythm it's waiting to be pushed at. So thanks for rocking springs back and forth with us all night. And until next time, when something rings or sways or trembles or won't stop swinging in front of you, don't just watch it move. Ask it the one question that runs this whole subject. What's the rhythm it wants?